What is up? Mine's Formula here. Gonna teach you all about statics. You ready? Alright, because I am. Skip. Next slide. Remember Phys 1? This is literally an extension of it. Boom! Crazy. You remember how Phys 1 shit moves? Not anymore. F equals ma, torque equals I alpha. Get out of here with that. Acceleration is equal to 0, angular acceleration is equal to 0. Boom! New equations. These two are really important. I would make sure you understand these two equations. They guide you through literally all of statics and more. Remember Phys 1? Oh, this box sliding problem of your kinetic friction that's driven by weight and the normal force and all that stuff? Well, that does move. So you have an acceleration. It slides down the ramp. You cannot use statics here. Another Phys 1 example. You literally have a pendulum swinging, right? Ding dong. The weight of the ball is driving it as a torque to the left with an angular acceleration. And the R is keeping it, pointing in a circular path the entire time. Anyhow, now statics. This is crazy. It doesn't move. Look, the box isn't moving. There's static friction. It's not moving. That's how simple it is. Big equation. You remember that disgusting I alpha? Well, guess what? Scrap it. Use the moment equation. Moment equation OP. R cross F. This one is looking weird with those vectors and cross products, but literally ignore the little squiggly above it. The cross turn into a multiplication sign, and yeah, this is what you would use in 3D. I will tell you. If you use it in 3D vector math, this is convenient. It can save you a lot of time, especially if you use any vector-based programming. Statics, sign convention, woohoo! Right hand rule. For you guys like this. Don't forget about that right hand. Okay? Thumb points in the axis, like about an axis, or a point. Like see point A? Point A is my point. I'm sticking my thumb out of the page, for me at least, or for you guys it's going to be thumb out of the page, and the direction my hand curls is positive. Another way to remember this is relative to that plane, counterclockwise is positive, clockwise is negative. And you can kind of see with the more 3D examples down below, my thumb is pointing out of the page at A and that, curl. Same thing with the negative. Do not use your left hand. Statics, reaction types, roller, pin, fixed. Those are the three, main ones in 2D. In 3D, there's a little more, bearings and ball joints and other stuff. Anyhow, with the roller, guess what? It rolls, but it can't go through the ground. So, skateboard is a good example. Roller support. Boom. Pin. You got a pin connection. It will hold things, but it won't move. You can think of it as a pin. It's literally a pin. It can rotate. Here's my finger. Ready? Look at that. It pivots. But big thing to distinguish between a fixed and a pin is you see how when I bend my finger isn't curving like that. It's because my knuckle is a joint. It's a pin. So if I do push it down, there's no bending moment at that point. Fixed. We have all three, right? We're going to have reaction forces in X, Y, and it also resists bending. Bending? What the hell's that? Well, a tree in the ground. When you see it get really windy and it bends the tree, that is a bending. If the tree was on a pin support, the thing would just flap over on its side. You get my point? Next slide. Big tips before we get into some math. Always draw your reactions with a positive sign convention. Super freaking important, okay? You have your X direction positive, Y direction positive. Draw them in that. They are positive for a reason. I'll explain why. It makes tracking your negatives way easier. Same with the moment. Use your right hand rule. Counterclockwise positive. Count the number of unknowns and knowns. This is really useful for solving when you get into big problems where you need to know if it's even a possible, system of equations. 6 unknowns, 6 equations. Check. 6 equations, 7 unknowns. That is statically indeterminate. That's what we like to call it, and you'll have to use numerical methods or make assumptions. One of the two. Or some cursed stuff. I don't know. It's magic at that point. Pick good points for moments. I'll explain this actually in the next slide. You see, so this is how the moments generally work. Okay, you have this angle bar, right? Now you have some force y and x right over here, right? Fy, fx. And they are going to create a moment at A. Well, how do I go about finding that moment? Well, you see the yellow dashed lines? Those indicate the line of action. So if I wanted to, I could take this fx, drag it all the way over to the dang right. If I really wanted to, for moments specifically, this is really useful because it makes it easier to visualize what that force is actually causing at that point. So at A specifically, I can drag Fy straight down, and my new, my lever arm that's easy to see is that bottom piece. Same with the Fx. And if that kind of makes sense with the vector math, the fact that, my R is in the Y direction, but the X is the Fx is entirely perpendicular to it in the X direction. So you get a perfect right angle, right? I know that was explained really weird, but it's a cross product. Anyhow, yeah, this is where I'm going to say pick a dang good point. I'm not solving this, but if you had to choose a point for your moment, where would you choose? Let's say F is given and the rest are unknown. Well, if I choose a point at A, I'm going to have moments from Fy, Fx, Hy, By. That is 4 variables right there. How many equations do I have? 3. Bad point. Boo. Out of here with that. What if I chose B? Well, guess what? Because it's on the line of action, Bx and By are 0. Same with Fx is equal to 0 and Hx is equal to 0. Fy, not Fx. Those are 0. They're on the line of action. They do nothing. They are entirely parallel, or however you want to think of it, with the cross product. They do nothing in terms of making a moment. But here we have Fx and Hy causing a bending moment. Well, guess what? We can do some solving there. My point is choose a point that gets rid of the most unknowns for your moment. That will help you solve quicker, faster, not catch an algebra mistake in your system of equations. It's just that much better. Next on. That was dragged out. Sorry. Now let's get into an actual example. Okay? Similar style. Whew. Pretty tough, right? Look at this. We got to find all the reactions at A. Dang, that's pretty tough, man. Well, look at this. You got some P, 90 kilonewtons, at some angle at point C. It is 3 meters in the X direction, negative X direction, and 1 meter in the Y direction. Well, how can we make this problem better with an FBD? Well, that is the point of those reactions. We are going to go from that fixture diagram to the FBD. Now, look at the FBD on the right. Looks amazing, right? You can actually solve that because you know your reaction types at your support. So now you have your reaction types. Well, what's the first thing you're going to do? You're going to start solving that sucker. Well, at point A. That is a really good point, okay, because it's a simple problem here. So we start with our 3 equations of motion in 2D. Sum of forces in the y, sum of forces in the x, and sum of moments, right? Sum of forces in the y is equal to 0. Look what's in the y direction. We got AY, and then we got the y component of P. So we multiply by 3 over 5 because that is a 3, 4, 5 triangle. Awesome, lovely, nice triangle. Then we have sum of forces in the x. We have AX, which is in the positive direction, and then if we look, the x component in P is in the negative direction. Big, big, big thing here. Always stick to the magnitude, like, of P. Never, like, if you were to look at this diagram and be like, oh yeah, P is actually in the negative x direction, it's negative whatever it is. That will put a negative sign in there, and it will make it'll actually make it negative 72 kilonewtons, which is wrong when you're trying to solve for, like what I'm trying to get at is, keep consistent notation. Use the magnitudes and don't change the direction of your arrows once you start solving. That is, if you do that, you will have no sign errors and you'll be good to go. And then with the moment about A. So this is putting the math to it from earlier. So you guys can follow a little bit better, hopefully. So how I like to do it is I like to create the F times R bit first, and then I assign a positive or negative. That is a way so you don't get confused and you always get the right answer, hopefully. So if we look here at this first component, P times 4 over 5. Look at our diagram. Well, 4 over 5 is in the x direction. So we bring it on that dashed line over, and our lever arm is 1. Well, guess what? That is simple as that, our moment. Well, guess what? That P is pointing in the counterclockwise direction. What does this do? Create a positive moment from our sign convention. Great. First term done. Now, second one. Let's look at the or x component of P. 3/5. We look at the y. Well, guess what? Now it's pointing up into space. Now we have 3/5 next to it, so we get the y component. And then 3 meters if we drag it straight down. Makes it easier to see. Guess what? When you bring it down there, it spins the bar in a clockwise direction. So it's negative. Or if you use right hand rule, it goes in the opposite direction, negative. And then you add your moment, reaction at A. Solve that, you get 90 kilonewtons meters. That is it. I hope that this makes sense. And refer to me if you need any more help. Ciao.